Alright, this is Chapter 3, Section 9, Inverse Trig Functions. Hopefully you kind of sort of in pre-cal. If you remember in pre-cal when you had, say, the graph of a sine function, that this cannot be, you cannot get an inverse because it's not one-to-one because of the horizontal line test. I'm touching the function in more than one place. So what we did is we just said, well, let's just restrict the domain from minus pi over 2 to pi over 2, and then within this particular domain, it is one-to-one. And so that meant we could actually have an inverse. Also, if you remember, the highs and lows of your sine was -1 to +1, and then if that's your range, that becomes your domain of your inverse, and then the range of the inverse is the domain of your original function. So hopefully this is like kinda sorta remember that a little bit. Let's hope. If not, this kind of stuff will be made available to you on the test. So a reminder of how we found values for inverses, because most of you did. And when you were in pre-cal, you were given this angle and you were asked to find this value. Well, for the inverse, you're on the unit circle. I'm looking for this value as y, because remember y was my sine, and I find square root of 3 over 2. So the question would be this one here, because there's also a square root of 3 over 2. Remember we said that the domain is from pi over 2 and minus pi over 2. So meaning you could only pick values within here. Okay, and once again, you're only looking at the y values, and as you can see, that's the only one that has a positive square root of 3. Alright, so we're going to go back and look at this theorem 3, which remember was the derivative rule for inverses, which basically said if you wanted to find the derivative of an inverse, the easy way was to take the derivative of the function and write it as a reciprocal. Well, if that's not always easy, then what you can do is you can take 1 over the derivative of the function times the inverse. So that's what we're going to do. And this stuff down here is just if I evaluate it at a particular point, and as you can see here, if I evaluate the derivative of the function at a particular point, I can get the value of the derivative of the inverse by just doing the reciprocal. This down here is just stating that you can find any place on this graph for the inverse, you can find tangent lines. Remember, that's what we're finding, derivative being slope. But you can't find it at these endpoints, because what's happening at these endpoints is you're going to end up with vertical tangents. And so most of you remember by looking at this, well, that would make sense, because if you're coming from the left side, your limits doesn't even exist. If you're coming from the right side, then you approach a value, so you have two different values. So if we want to find what the derivative of sine inverse is. Well, I know what my original function was. My original function was just sine of x. So what I could do is I could use that theorem 3 that says I could find the derivative. I don't know what I'm doing. I could find the derivative of the inverse. Made that work, didn't I? And so in other words, I could find this derivative. Theorem 3 says I can do that by writing 1 over the derivative of my function times the derivative, or times my inverse. So this is my original function, and then this is just simply my inverse. So that's easy enough. I can plug this stuff in. The derivative of sine, of course, is cosine. And then I just simply write my inverse. You don't know how hard that is to write a -1 that small. And so I just write my inverse. Well, we'd kind of like this to just be in terms of the variable x, not with this sines and cosines. So I go back and I say, well, I remember this whole deal of sine squared x plus cosine squared x equals 1. I could solve this for cosine, meaning cosine of x equals the square root of 1 minus sine squared x. And I could plug that in here, and where I see x would be my inverse. So going to the next step, I would have 1 over the square root of 1 minus sine squared. Where I see an x, I put my inverse in there. And then, hopefully, you kind of sort of remember, let's write it up here. If I have a function and I multiply it by its inverse, this equals just that value inside there, meaning x. So this piece right here, because it's squared, is just going to become x squared. So I'm going to end up with 1 minus x squared, all square root. So you'll find this on your page of formulas that says, therefore, the derivative of the inverse sine equals 1 over square root of 1 minus x squared, but wait, there's more, times the derivative, in this case, of that value inside. Remember, by the chain rule, you do not want to forget that, because that may not always be just an x. So just remind yourself that, oh yeah, so I've got to also take the derivative of the inside. So we're going to just use this definition now to simply work eventually when it loads. Okay, so I want to find y prime. I can do this either the fast way, my way, but now you're going to see as these get a little more difficult, it's a little bit easier to do that whole u, y thing, meaning that I could let u equal the square root of 17 times t, that t's on the outside, and then I can take the derivative, which the square root of 17 is just a constant, so that's just u prime, is square root of 17, and then my y then would just equal sine inverse of u, and my y prime, we just found, we said is 1 over the square root of 1 minus u squared. So all I'm doing is using the chain rule here, which says now I take these two pieces and multiply, so that becomes a square root of 17 over 1 minus u squared, and then remembering what u equals, I plug that back in. Square root of 17 over square root of 1 minus square root of 17t squared. And if you want to make this look a little bit better, you could go ahead and square the square root, and you could square the t. And that would be your final answer. So as you see, we proved this using Theorem 3, but now you're just going to start using this definition right there to be able to find these derivatives. All right, let's figure out, well, what is the derivative of the tangent? We can do it the same way. Again, we know that, well, my original function, if I have an inverse tangent, was just the tangent. So again, by Theorem 3 says, let's see if I can write it right this time, if I want to find the derivative of my inverse, then I do that by writing 1 over my function, which is, the derivative of my function, and this might be an extra step you want to write up here. So the derivative of my function, you remember this one, secant squared x, so that becomes secant squared, and then my x, what's inside the parentheses here, is going to be my inverse, which is tangent of x. Well, if you remember on the other one, we said, well, we had sine times sine inverse, and that canceled out. So in a perfect world, we would like that somehow to be a tangent. And we all remember our identities, right? That's what I thought. So in other words, our identity says secant squared u equals 1 plus tangent squared u. Okay, so this is an identity. Identity. Alright, so I'm going to come over here and rewrite this. So where I see secant squared, I'm going to put 1 plus tangent squared. In my parentheses is going to be my inverse. And then just as we did before, we can see that this cancels. Don't forget that square. So I'm going to end up with 1 plus x squared. So in other words, therefore, the derivative of the inverse tangent equals 1 over 1 plus x squared, not forgetting the chain rule, and then times the derivative of that inside piece. So we're going to use this to actually work a problem. If I want to find this derivative, again, I'm going to kind of break this down and say, well, my u is the square root of 7t. Now, all that is under t. I really, really, really hope you have gotten this down, how quickly you can find this derivative. 1 over 2 square roots of 7t times the inside derivative. So the derivative of the inside, 7t, is just 7. Okay, so I really, 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 really hope you have that down. Remember, that's the square root of x. Its derivative equals 1 over 2 square roots of x times the derivative of x, which in this case was just 1. So I got that piece. Now, get all this junk out of my way. Because you got that, right? You're saying yes, hopefully. Okay, so then over here, I'm going to have my y equals my tangent inverse of u. And so my y prime we just found is 1 over 1 plus u squared. So that makes this pretty easy to work these. So now if I want to find this derivative, dy dt, it's going to equal 7 over 2 square roots of 7t times 1 over 1 plus, well, let's just go ahead and plug in what u is. Where did I get that from? Rock chair. And then I can make this look a little better. I could, certainly square this out. So 1 over 1, oh, I guess I got to write all that other junk first. New line. So equals 7 over 2 square roots of 7t. All I'm doing here is just going to square that square root. So I'm going to end up with 1 plus 7t. And that's pretty much your answer. I mean, if you want, you could rewrite it as 7 over 2 square roots of 7t, then times 1 plus the 7t. Just for the way my math lab would want it. Now, of course, we did the sine, we did the tangent. You could go through all of these and prove them that same way, or when cool, you can use these inverse cofunction identities. Maybe you remember these, so these are more identities from pre-cal. And so you could just use these. So let's say I want to find the derivative of the cosine inverse. And instead of using that theorem 3, what I'm going to do is I'm just going to use this identity, which says, well, that would just simply equal the derivative of pi over 2 minus sine inverse of x. I can split up this derivative, pi over 2 minus the derivative of sine inverse of x. Well, pi over 2 is a constant, so the derivative of a constant is 0 minus, we already know this one is 1 minus x squared, and thus, therefore, the derivative of the cosine inverse equals the negative of 1 over square roots of 1 minus x squared. Okay, so certainly you could prove every one of these, and then you get a sheet,
and here's all the actual ones. This du dx up top here is just where you saw me multiply it here to the side, so this is just chain, all that is chain rule stuff. Okay, so as you can see, we did these first three, so certainly you should be able to manipulate these others and do them. And now what we're going to do is an example using this secant. So you can see you're basically just plugging things in. So I want to find this derivative. My definition says that the derivative is going to be 1 over the absolute value of u, where that's your u. That's why I said it's a good idea that you've learned to say the u is what's inside the parentheses, and then the square root of u squared minus 1, and then times this derivative. So this is going to equal 1 over absolute value of 2s plus 1 times the square root of 2s plus 1 squared minus 1 times the derivative, what do I got, s is going on here, times the derivative of the inside. Okay, so that's that piece. So as you can see, the derivative of the inside is just 2. So I'll write that 2 up top, 2s plus 1. I'm going to go ahead and square out the bottom, and you'll see why. So I get 4s squared plus 4s plus 1 minus 1. That's the reason why. That cancels out. Alright, and so now I have this business, 2s plus 1 absolute value. And now what I'm going to do is I'm going to actually factor out a 4 in the bottom. So I get s squared plus s. And what that allows me to do is to take the square root of 4, which is 2. And this is all still under square root. That cancels. And so I end up with my final answer of 1 over absolute value of 2s plus 1 times the square root of s squared plus s. So that allows me to make it the way, you know, my math lab likes it. Alright, now when you're doing the homework of finding limits, the easiest way is to look at the graph. So this limit. Okay, and you thought limits were over with, huh? That's what you get for thinking. Alright, so this says as x approaches 1, let's find 1, that minus sign says from the left. So here I come, I'm approaching 1. What is the value of my function approaching? And the value of my function is approaching pi over 2. So if you have these graphs, that's why I said I have these available to you, these are pretty easy to do. Then if I'm looking at the secant as x is heading out to infinity, what is my function doing? Well, my function is getting closer and closer and closer to pi over 2. And so that's how you find these limits. Now, one last mention is this is actually used, Newton used it in something called Newton's serpentine. What I would like you to do is research this, and you'll find a YouTube video that shows it. And to be able to show that y equals 4x over x squared plus 1 is identical, the graph, to y equals 2 sine times 2 tangent inverse of x. Okay, so in other words, just graph both of them. And then I want to know why and can you prove this. And bring this to your test number 2. So if you want to do this, meaning it's extra credit, then bring it to your test.